What specific problem does your proposed vocabulary parallelism method aim to solve in the context of pipeline parallelism? Can you detail why this problem is significant?
The proposed vocabulary parallelism method aims to address the imbalance issue in pipeline parallelism, PP, caused by vocabulary-related layers, which is often overlooked but significantly degrades performance in both throughput and memory. This problem is significant because, in typical PP setups, the first stage contains an additional input layer, and the last stage has an output layer, leading to an uneven distribution of workload and exacerbating memory bottlenecks, especially as vocabulary size increases. For instance, in the case of a large model like Gemma 29B, with a vocabulary size of 256K, the output layer's computation and memory requirements can be approximately 5 times greater than those of the transformer layers, highlighting the severity of the imbalance. By partitioning the vocabulary layers across all pipeline devices, vocabulary parallelism effectively balances computation and memory usage, resulting in up to a 51% improvement in throughput compared to naive layer redistribution methods. This approach not only mitigates the memory bottleneck, but also enhances the overall efficiency of training large-scale models.
Can you describe step-by-step how the vocabulary parallelism approach works? Please outline the main components and their interactions.
The vocabulary parallelism approach works by partitioning the vocabulary layers across all pipeline devices to balance computation and memory usage in pipeline parallelism, PP. First, the vocabulary layers are evenly distributed across the devices, allowing each device to perform computations independently during the forward and backward passes. This partitioning introduces several computation passes, denoted as F_1, F_2, and B, which are separated by all reduced communications that manage dependencies across devices. To optimize the number of communication barriers, the approach reorders operations within the output layer, reducing the communication overhead from 3 barriers to 2, thereby minimizing activation memory consumption. Finally, the vocabulary passes are integrated into existing pipeline schedules, ensuring that the scheduling adheres to dependencies while maintaining a small constant overhead in peak activation memory, ultimately leading to improved throughput and balanced memory usage across devices.
Can you illustrate with a simple example how the proposed algorithm works? For instance, consider a hypothetical scenario with specific numbers and stages in pipeline parallelism.
To illustrate the proposed vocabulary parallelism algorithm, consider a hypothetical scenario with a pipeline parallelism setup involving 4 devices, D1, D2, D3, D4, and a vocabulary size of 256K. In this setup, the output layer is partitioned across the devices, allowing each device to handle a portion of the vocabulary. For instance, D1 processes the first 64K tokens, D2 handles the next 64K, and so on. When a microbatch is processed, each device independently computes its forward pass using its local vocabulary partition, which reduces the need for global communication. The algorithm optimizes the communication barriers by allowing devices to compute local softmax values using their maximum and sum, thus minimizing the number of all reduce operations from 3 to 2. This results in a significant reduction in activation memory overhead while maintaining high throughput. For example, if the naive implementation resulted in a peak memory usage of 45 gigabytes, the vocabulary parallelism approach could balance this across devices, leading to a more efficient memory usage of less than 2.5 gigabytes difference across devices, demonstrating the effectiveness of the proposed method.
What are the key advantages of using vocabulary parallelism compared to existing methods such as zero, tensor parallelism, or naive layer redistribution? Please provide specific metrics if available.
The key advantages of using vocabulary parallelism, VP, over existing methods like zero, tensor parallelism, TP, and naive layer redistribution are primarily centered around improved throughput and balanced memory usage. VP effectively addresses the imbalance caused by vocabulary-related layers, leading to up to a 51% improvement in throughput compared to naive layer redistribution. Unlike 0, which suffers from high communication overhead, and TP, which faces low arithmetic intensity and significant inter-device communication, VP minimizes communication barriers and overlaps operations, thus reducing activation memory consumption. Additionally, while naive layer redistribution still results in significant performance degradation, 8% to 33% drop in MFU for large vocabulary sizes, VP maintains a steady MFU and achieves balanced memory usage across pipeline devices, with peak memory imbalances reduced to less than 2.5 GB. Overall, VP provides a more efficient and scalable solution for training large models with extensive vocabulary sizes.
How did you validate the effectiveness of the vocabulary parallelism approach? What experimental setups, datasets, and performance metrics did you use to assess its success?
To validate the effectiveness of the vocabulary parallelism approach, we conducted extensive experiments comparing it against several baseline methods, including a naive implementation, layer redistribution, and an interlaced pipeline. We pre-trained GPT-like models of varying sizes and vocabulary sizes, using up to 32 NVIDIA A100 GPS across 4 nodes interconnected by a ROS RDMA network. The performance metrics assessed included throughput measured in flops utilization, MFU, and peak memory usage across different pipeline devices. Our results demonstrated that the vocabulary parallelism methods consistently outperformed the baseline by maintaining a steady MFU and achieving balanced memory usage, even as vocabulary sizes increased. Specifically, we observed improvements in throughput of up to 143% compared to the naive implementation, while also addressing the memory imbalance issues that arose with larger vocabulary sizes.
What limitations or potential drawbacks did you identify in your proposed method? How might these impact the practical application of your approach in real-world scenarios?
In our proposed vocabulary parallelism approach, we identified several limitations that could impact its practical application. Firstly, while partitioning the vocabulary layers across devices reduces memory overhead, it introduces additional communication barriers, particularly during the softmax computation, which can complicate pipeline scheduling and increase activation memory consumption. Secondly, the method incurs some computation overhead due to the partitioning of vocabulary layers, which can reduce the model's flops utilization and may lead to less efficient GPU kernel operations. Additionally, the effectiveness of our approach is contingent on the model and pipeline parallel settings, which may limit its flexibility across different scenarios. Lastly, while our method shows improvements in throughput and memory balance, it still requires careful management of communication streams to avoid performance degradation, particularly in multi-node setups. These factors could hinder the scalability and efficiency of our approach in large-scale real-world applications.